Okay, here we have a challenging problem that combines many concepts students learn over the course. Let's read the problem first. A massless spring of constant is fixed. We have a spring constant on the left side of a level track. A block of mass is given as zero point 0.5 kilogram is pressed against a spring and compresses it a distance d. The block initially at rest is then released and travels toward a circular loop-the-loop of radius r. We got the radius of the circle. The entire track and the loop-the-loop are frictionless except for the section of track between points A and B. Given that the coefficient of kinetic friction between the block and the track along AB is, we have kinetic coefficient, and that the length of AB is 2.5 meter. Determine the minimum compression D of the spring that enables the block to just make it through the loop at point C. This is our final reference point, and this is our initial reference point right there. Here's our hint. The force exerted by the track on the block will be 0 if the block barely makes it through the loop. In other words, it's saying normal force equals 0. We are looking for the minimum compression D. That's our goal. So D minimum will be meter. Let's write down all the necessary information. Okay. We have our main equation. Thing is, as we press this, and that stored energy will be converted to kinetic energy, but some of them will get lost to the environment. And then it's gonna go through our frictionless track and undergoes the circular motion. And we expect the normal force at the point C equals 0. Then I can define E. Change in energy is E final minus E initial equals non-conservative. Notice that we have 4 energy. Let me write it down. Kinetic energy here. Actually, potential energy due to spring, and then it undergoes kinetic energy. And then we have potential energy due to height, and we have the non-conservative energy here. So I'm gonna write kinetic energy plus potential energy due to gravity plus potential energy spring final minus kinetic energy potential energy due to gravity and potential energy due to spring initial. Let's cancel out things we can. Potential energy initially, I'm gonna set this to be y equals 0. Then there's no height involved in our, the potential energy is mgh, height becomes 0, so our formula goes 0. Kinetic energy initially is 0 because our problem stated that initially it's at rest. Then we can cancel out the potential energy at the point C because the block is no longer attached to our spring. Then I can write down each energy in more refined. mv squared. Okay, I'm gonna put t because our tangential velocity will be same as our final velocity plus mg. Now notice that at point C, we have two r, one r here and another r here. Okay? So I'm gonna put 2r minus spring potential energy. Make sure you put d squared. Now I can write non-conservative energy more refined. We're gonna have a force of friction times the distance AB. Our motion is toward this way, but the frictional force is the opposite. So we're gonna have minus sign in front, and this is normal force times the coefficient. The normal force here will cancel out with the force due to gravity. So I'm gonna write mg times the 2.5 meter of distance from A to B. So that's gonna replace our W and C there. Then we have to find the tangential velocity at the top. Okay, I'm gonna draw the force body diagram. We have force due to gravity, mg. There's a normal force perpendicular to this track, but then remember in our hint the n equals 0, so I'm not gonna rewrite that down. And we have centripetal force toward the center. You see the center here is aligned with our point C, so AC. In other words, we can have mg equals ma, the centripetal acceleration. I can rewrite acceleration as vt squared over r, and then notice that our m cancel out. Then we multiply r on both sides. I'm gonna leave it at the vt squared because we have vt squared in our main equation, and simply plug this in where? Here. So let's finish our equation. Remember, we're looking for D, so I'm gonna place this to the other side so that I have positive. So, and then I'm gonna push this to the right side and change it the sign to positive. Then I get okay. I can multiply both sides by 2 and then divide by k for now. Then I'm gonna have d squared on the left side. I have mgr over k plus 4mgr over k plus 2 mu mg ab. Okay. Do you notice that our mg's can be factored out? And I'm just gonna write big. I'm just gonna have a 1k in the bottom. So mg is pushed out. Okay, we have 4r and then r. So 4r plus r is 5r plus 2 mu k ab, distance ab. Now we're gonna square root this. And then plug in our given variables. D minimum is equal to, mass was 0.5 kilogram times, oh, don't forget the gravity constants, 9.8 meter per second squared, and then 5 times the radius of the circular track, 1.5 meter, plus 2 times 0.3 times 2.5 meter, or divide by our k, the spring constant, 78.4 Newton per meter. Don't forget the radical sign above it. Okay, when you punch these numbers in your calculator, you're gonna get 0.75 meter. And that's our answer. Okay, so if you press 75 centimeter here, okay, it's gonna convert to kinetic energy and lose some to the environment, and then undergoes the circular motion, and when the normal force equals 0, so it barely is attached to the track and then finish or exit this way. Okay, that's it, and thanks for watching. I will see you next time.